差一点啊，讲者也是英文的，所以待会儿可能要考验一下大家的专心程度。那一样哈，大家准备一下，我们随时要开始了。OK， 好，那我是今天的主持人，我叫丽书。那有几件事先做一下事先的宣导。哎呀，长度正头了。好，第一个网络的使用，这个在每个地方都一样。我们有3个 AP 在这一间会议室里面，麻烦你依照你的座位哈，最好不要互相冲突啊。啊，有3个 ID， 你可以自己选择一下。那另外呢，还有就是在大会规定啊，应该说这个场地规定，请不要在会议室里面饮食。他有给我们一个开放的机会，就是讲师可以啊，其他人如果你觉得愤愤不平，欢迎报名，下次我们安排你上来，你就会享有这个特权。好，那另外一个当然是一个礼貌的问题，请你把你的手机关机或者形成震动。那经过昨天一天的经验，我们发现似乎在会议室里面你也不太能接手机，因为收讯太差。好，然后展示一下，因为是7月，所以你不要说亮，这个广告不知道跟我们看过，网络上流传的，吵什么鬼啊？千万不要这样子哈！现在是飘飘乐。好，那接下来我们就要准备一下，把你的热情展现出来。我们需要各位的，好，你看，如果没有这个反应，我们会切到下一张投影片。你如果看到这一张，也是一样要做一样的动作。那接下来，来宾请掌声鼓励，欢迎我们的讲者 Holger Freyther。
I think I'm supposed to start. Good morning. I'm talking about the GNOME Memory Profiler. It was not created by me, but I thought it's useful, and so I've opted for maintaining it and developing it further. I'm pretty sorry this is going to be a technical talk, and if I'm losing anyone, we can try to pick you up, but it might or might not work. But you can get in touch with me later if you still have questions. So our agenda is first of all figuring out what the GNOME memprof is actually about, and then we will look in how it's working. So we will have to see how C applications allocate memory. Then we need to figure out how to get a backtrace to see who was allocating the memory. This leads us to the problem: how do we intercept a function call to an external library, and how to get a backtrace from this. And finally, we are concluding with a backtrace. So, what's the summary? So, what is GNOME memprof? It's a tool to analyze the memory usage. We can visualize the allocations to see how much was allocated over time with a time graph. We also have a view done by someone else to visualize memory fragmentation, which works nicely if you only have a small program, but in case of WebKit, it's going to be so slow that it's currently unusable. And to not make it as dry as possible, I'm actually just showing you the application. So I've started. I've started the GNOME Memory Profiler, and this is the application, and I'm looking at events. So right now I have allocated everything in memory from this bar, and this one was actually mapped but is currently returned, and I do have this graph. So over time we see startup, we have a small peak, and then we free some memory, and then we're going up again, and here. So if I'm opening any file, do I have something in my history? So if I'm opening these slides of my conference, we see that it actually allocates a lot more memory in peak, and it displays the window on the different screen. So we see that just by opening, we do have this peak in memory to open the PDF, and then it goes down, and then it goes back. And we can press profile to actually generate a profile of the application, which is now going through all all allocations, and it's going to visualize them. So we can see in self how much memory was allocated in each function. So the pixmem image crate bits has allocated that many bytes. You have to divide by yourself to get the number of kilobytes and megabytes. So and you see that crate bits was calling pixmap image allocate, and in the caller view you're actually seeing who was calling this function. And by double clicking you can see this graph extends, and you see the possible callers of this function. So Cairo image surface crate was actually calling pixmem. So we can click again, and we do see that Evins has been loading a libpdf document plugin, and right now it doesn't know anything about it because I don't have symbols for this backend. So just by clicking here, I'm not going to have a lot more information. I'm just seeing that events, document render, document load, and document thumbnails have all allocated memory. So if you have debug symbols of all your libraries, you can trace back every allocation of your application and be able to see who is the main offender, and if you see it. There's also a leaks display which uses the Böhm GC algorithm to find out which memory was leaked, but I actually think it doesn't really work. We have seen the time graph, which is actually now stable, so it doesn't leak more memory or allocates more memory over time. And we do have this graph which actually shows you which areas of memory were allocated, and like here's the stack, here's the heap, and which actually we're missing a legend to explain which colors are used for which kind of things, but you can actually, if you know the colors, figure out which areas of the memory are allocated or were unallocated but not returned to the system. So if you have a lot of places where you have had memory allocations but the block is too small to return it to the system, you can see it here and probably do something about it by using gslice or just allocating memory in the same sizes. So I'm just going to quit this application, and now we're going back to the slides and figure out how it's actually working to do this. So memprof works by tracking calls to malloc, new, gslice, and other things. It generates a backtrace for each allocation, and it forgets about the allocation when it's freed. So the biggest limitation with this approach is that an allocator actually works by allocating memory from the kernel, which is either using mmap to allocate an anonymous non-shared piece of memory, or the sbrak call, but this is not intercepted by memprof. So if you use a custom allocator in your application and it doesn't have external linkage and all calls go directly to this custom allocator, you're not going to see the allocations in memprof. This is an example of problem with WebKit where we have a custom allocator which has internal linkage. So you're only seeing half of the allocations that your application is really doing. But if you're aware of this problem and you know you don't have a custom allocator, it shows you every allocation your application is doing. So the memory allocators like glibc or others actually use these two calls, but we're not interested in these to allocate. So we are only caring for malloc, free, new, delete, and allocate arrays and delete arrays. And we also have some special knowledge for gslice and others to generate a more meaningful backtrace. So we know of glib functions that allocate memory and start the backtrace at this function instead of the malloc call, which is done from the allocator. So how do I find calls to malloc? One approach would be to to change every call from malloc and make it call a new function and make it call a new function and try recompile the result, or I can try to instrument glibc to build a custom glibc which calls my application, but in general both approaches are not practical. We want to look at the memory allocations of an existing application right away without recompiling the system, so we need to have a different way. So the way is to use a ELF feature to preload symbols. So I don't know. So how many of you have ever used LD preload to load a library? Anyone else? Do you know the concept, or? So the idea is to So the idea is to create a. Let me switch again. So the idea is to just let me switch the colors off. So we just write a small application to preload a symbol. So we want to have our own implementation of malloc instead of the other one. So we need to remember the actually malloc call. So I call it real malloc, and it's a function pointer having the signature of malloc. And then I'm providing a malloc function with the same signature as used by the system. And in here I can check if real malloc, like so if real malloc is 0, I will have to find the real symbol of malloc. So I can write it like this: real malloc, assign it to dlsim, and there's a glibc function called, or a special handle for the dynamic linker, which is rtld next, which helps me to find the next symbol called malloc. So I can write it like this, underscore. And luckily my current glibc doesn't allocate memory, so I can use a printf from inside the malloc function. If it would allocate memory, I would have like an infinite loop and it would crash, so I can write real malloc here, and at the end I'm just calling the so at the end I'm just calling the real malloc function with my member, and then I need to compile it as a shared library. I'm calling it libpremalloc2so. One has to use position independent code because we're preloading, and then I'm handing it the source code, and it doesn't know about rtld next, so I will have to go back here. First, it's a GNU feature, so I need to define GNU source, and I need to include a header file called dlsymbols, and I need to write it properly as well. So of course it's called differently, so I'm using the man page to find it. So it's warning that it does know my printf. I should include standard IO to have the right signature, but I'm lazy. And finally, I can use LD preload SO, and now I can execute any other application which allocates memory. So ls would be the most simple application to execute, but it doesn't allocate memory at all. So we have to go for something else. And it refuses to work, cannot be preloaded. anyone sees what I'm doing wrong? One? A bit too much. But actually I can just cheat and use the stuff I did yesterday, which is about the same. It's ignoring it too. So I didn't change anything in my system and it's ignoring my library. Libpreload too? Yeah, I compiled this one yesterday, so I have 2 SO files in there, or actually 3. Yeah, but well, I tried this one before, but it. Sorry? Absolute pass for the library. All right, good point. And we see that real malloc is getting called. And we have learned something, so we need to use an absolute pass. I don't remember that I did this yesterday, but so we have done the first thing to have a custom allocator. We just need to define the functions we want to change and remember the real name of them and then call it. So the next thing is to generate a backtrace, and because I don't think I have so much time, I'm just going to show you the ways of generating a backtrace. And let's. So on glibc systems to generate a backtrace, we can use a built-in function in glibc called backtrace or backtrace symbols. And to make it work on ARM, you need to compile your application with -f no or mid frame pointers. Otherwise, the system doesn't know where a frame ends or stops. On x86, you don't face the same problem. Or if you're using GCC, you can also use like one of the built-in functions to give you the frame address and the return address of a stack frame. Or I think there's called a library called libbacktrace, which works on many platforms to allow you to generate a backtrace as well. Or if you're really fancy, you can do it yourself and try to walk the stack. Just figure out the stack layout and find the return pointer and walk the frames. Yeah, but once we have walked the frame, we have a list of, actually I think, say program counters, but in this case we're going to have the pointers to the text segments. And so I have a simple application. Let's go through the functions first. The first one is called generate backtrace. It's getting called from bar, and the function foo calls bar, and bool calls foo, and finally someone calls things. So I try to generate some calls to have a stack trace. And inside the backtrace, at first we're using glibc as a simple feature to generate a backtrace. Just allocate a buffer of void pointers and tell glibc how many void pointers we have, and then iterate over the list we got back and print them. The next one is to use symbol names. So if you have enough debug information, glibc actually can print out the function names itself. And finally, we're using the GCC feature to give us the address of the call frames. So actually, we know where we return to. So if I compile with debug information, if I compile with debug information, we're actually seeing with glibc plain functions, we see the address of the text segment and where it was. With symbols, it actually only knows the binary name, but not the function name. There's a special GCC function to generate more information, and we could even see the function names inside the binary. And with the GCC built in, we actually see the same address for return address. So we have many ways to generate a backtrace. But if I give you an address, you actually don't know which function was called. So does anyone know how to get the file name and line number from an address of your text segment? No? Anyone? You probably do. Hmm? Oh, another application from BenUtils. Another one. No, it's just actually a really simple thing. Address to line. We tell it, or actually, it's very simple. You pass it the application, you tell it that you want to have the function names, and you finally give it the address. So we want backtrace 2. And we want to know which function is this, and so it tells us it's backtrace C and line 38. I've never verified it works, but yeah, so it figures out it was Bar who called this thing. So now we have three things. The first one is we know how to intercept calls to malloc. We know how to generate a backtrace. The next thing that we actually need to do is translate names, like the point or the address to a name. And in memprof, you're using like libbfd from BenUtils to do this. It also can demangle C++ names into names normal people can read. But I'm not going to show this part. So, yeah. So with libbfd, one can translate the address back to a meaningful name. As a small summary for this, we have seen how to use LD preload. We need to have an absolute path for the library when we want to load. One can use libbfd to get shiny names, and there are many ways to generate a backtrace in your application. So if you want to have some kind of automatic crash report, you could handle zigzag-fold and use one of the ways to generate a backtrace and lock it somewhere in your application if you don't have a different or better way to generate cordons. And memprof is using all this and builds a UI on top of it. A small outlook, like if you're interested in using it or improving it, it currently doesn't work on ARM because we don't generate proper backtraces for it. We have a problem with custom allocators, as I told you. We need a way to fix it, and there's also for the last couple of years there's a system in development called SystemTab, which could allow user space tracing if utrace ever gets merged to the kernel, and memprof could be built on top of SystemTab to get this information, and this would also solve the problem of custom allocators if I understand things correctly. And before I finish, we can go back to the actually memprof code to see that the stuff that I talked about is actually the stuff I'm doing we're doing in memprof. So we have two parts. One is like the lib directory, which has code for stack frame, which is actually yeah, it's not done by me, so I'm building on top of the work of others. So the first one here is just using glibc backtrace feature to get the backtrace. The next one actually knows about the stack layout on x86 and knows the place of the return address and starts with the first frame and then is walking the frame until the end of memory. Here, and if we don't have it, we just error in compilation. And mem-intercept is the same. So as you have seen in the example, we have custom memory pointers, some special code for WebKit, and inside do malloc we see if we have invented ourselves, and then we call the real address. We remember which kind of abbreviation we did, the old pointer, the new pointer, how much we have allocated, and then we generate a backtrace from this place. And it's getting written over a Unix domain socket. And then in the source directory, we have the usual GDK code to have a tree model and navigate through it. Okay, I know this was a lot in just 30 minutes, so do you have any questions or doubts, or did I lose you? Did you understand? Or
各位如果有问题的话，请踊跃发言。那发言前提醒一件事情，请先按一下你桌上那个开关，我们才听得到你的问题，好 ，Freyther 才知道你在讲什么。好，麻烦有任何问题的话，可以现在发问。啊，如果你觉得害羞的话，等一下 Freyther 还是在那边，你可以跑过去问他也可以。哎，那看现场有没有直接想要跟他做互动的。
Please go ahead.
也对，看起来讲者比我们还要害羞。好，我们可以教他一句中文叫沉默是金，因为我们现在大家表现都是黄金的样子。
Does the memprof support the memory debugging features? For example, the check if the memory is accessed after it is freed or is no?
Not at all. It just tracks allocations and allows you to see what was allocated.
Thank you.
Hello. Is it the front end of anything?
Sorry?
Is it the front end of anything?
It's either front of
Front end.
Front end. Do anything. Yeah, it's the UI. You can navigate through the allocations. It's it tries to resolve the symbols to names. Oh no, it's everything included. So the library is part of memprof as well.
Okay. Thank you.
How is the performance compared to other memory leak detector such as Fargrind or something else? Because we have to run memory detector on some heavy loading servers, so performance is an issue.
Yeah, I think the leak detection of memprof is not really working right now, but in general it's faster than Valgrind because it's not emulating anything but just intercepting calls. So if the leak detector would fully work, it would be faster than Valgrind.
Thank you.
这时候是要拍卖喊价的时候，第一次，还有没有问题呢？再来第二次，那我们要 deal 咯。那这时候我们要谢谢我们的讲师给我们一个这么精彩的演出，还有实作。那这时候应该，通常应该大家有反应啊，还是我要把这个，对 ，show your patience。那我们谢谢讲师。好，那我们也请大家稍微休息一下，我们也没有休息多久了，我们等一下下一位讲师过来 stand by。